focus on exponential growth and decay in this lesson. I know I introduced those terms last week briefly, but we're going to go into much more detail now. So remember oops, get my pen here. The general form of our exponential is to have some base b raised to the power of x. That's what makes it exponential, is that x is in the exponent. We talked briefly last week about the b value, the base, determining whether we have growth or decay. We said that if that b value is greater than 1, okay, the function is going to be exponential growth. And you can see that example over here. Okay, so you can see that it is greater than 1, so this is exponential growth. The graph is increasing from left to right. Okay, and then we said that if that value is between 0 and 1, that will represent exponential decay. Okay, and you can see graphically over here, exponential decay, you can see your b value in this example is 1/2. So that's between 0 and 1. It is decreasing from left to right. So I would actually encourage you to add those words. Okay, increasing and decreasing. That's what you're looking for if you're looking at the graph to determine if it's growth or decay. If you're looking at the equation, you're checking out that b value. Is it greater than 1 or is it less than 1? Between 0 and 1, I should say. So here, take a second and try these. You should be watching this as a video. This isn't live since I'm out at the regional golf tournament. So pause the video real fast and try this matching, and then we'll come back and check it. Okay, if you're back after pausing, what we're looking for is matching these graphs to their equations up here. So let's see. We can say right away, this is greater than 1, so I know this one's going to be growth. This is greater than 1, that'll be growth. This is less than 1, 1/4, so I know this one will be decay. And 0.7 is between 0 and 1, so that will be decay. So I've narrowed it down to which two are growth, which remember, that's increasing left to right. So I can see right away here, this one is growth, because it's increasing left to right. And this one is growth. And these two are both decay, because they're decreasing left to right. Okay, so now we just need to match which was which specific equation. So remember, we talked about last week when that b value there, that base value, the higher it gets over 1, the more steep the increase, the more quickly it's growing. So 3 is greater than 1.2. So 3 is going to be this steeper one over here. And you can also remember, you could plug in points if you didn't know. If I were to plug in a 1, 3 to the 1 power is 3. So there should be a point at 1, 3, which there is. Okay, so this is that B equation. Okay, and then this one was less steep. It was increasing at a slower rate, and that is the A graph. And you can also see at 1, it crosses at 1.2, which is the base. Over here, these are both the decay graphs. Now this one is, you can do the same thing that we talked about, like plug in a 1, so there should be a point at 1, 1/4, which you can see here. And this one should be a point at 1.7. You can see that's a little higher, closer to 1 where it's crossing. But it's also, you can look at the steepness. So when you're looking at a decay graph, you're looking at that b value. The closer that b value is to 0, so it's like the further away from 1, the steeper the exponential will be. So 1/4 is further away from 1 than 0.7. So it's got this steeper decline. Okay, so that is your C value, and that one is your D. All right, let's go ahead and flip over. On the back, we're going to look at real world situations where exponential equations can model the situations. Okay, so you have exponential growth and decay, which is going to most often be determined by a percentage. So if we're talking about things like interest being earned or charged, so we're talking about accounts, bank accounts, things like that. You may also see exponential growth or decay in scientific settings like measuring bacteria and disease growth and things like that. So there's lots of different real world scenarios that exponential functions can represent. So this function shows you when we have our equation, our A value represents the initial amount. So I'm going to try and color code this. So this is your starting value. Okay, so the amount you start with, whether that's money or bacteria or whatever, the starting amount, the initial amount. Now, what we call the growth and decay factor is determined, it's a percentage growth. And so if we think about percents, 100%, when we convert percents to decimals, remember we move the decimal 2 places. So 1 represents 100%. So you have the 100% that you started with, and then plus or minus tells you whether it's growth or decay. If it's growth, you'll have a plus. If it's decay, you'll have a minus. And then R is the rate, okay, at which it's growing or decaying. Okay, so we determine our growth or decay factor by doing 1 plus or minus our R, which is our rate. Let's fill this in over here. So if it's 1 plus R, that is called the growth factor because that will make the base greater than 1. So it'll be growth. If you have 1 minus R, that is called the decay factor because if you start with 1 and you take it away, you're going to have something less than 1. So it's going to be between 0 and 1. Okay, and then the other values in your equation, you'll see the exponent, which normally we see that as x, our variable. We're going to use t because it represents time. Okay, so our time is going to be our variable in the exponent, that our growth factor is raised to the power of t. Okay, and then of course y, what we come out with, that's the amount you have after the given set of time. Okay, now what we're going to be focusing on is just setting up these equations. We don't even have to solve them. If you are given an initial amount, a growth or decay rate, and a time period, it really is just making sure you plug everything in correctly, get your decimal from your percent done, converted correctly, and then you can just plug that into the calculator and pop out your Y value, okay, what your amount is after the fact. Okay, but we're not even going to ask you to do that right now. I'm just going to focus on setting up. So to set this up, it says the annual number, for example 2A here, the annual number of Lyme disease diagnoses in California has been increasing by 40% each year since 2015. Okay, so right there, that is my rate. That's my R. Okay, 40%, and it's increasing by 40%. Since 2015, when 250 cases were diagnosed. So that's our initial amount. We're starting initially in the year 2015 with 250 cases. So that's our initial amount. It says write a function representing the number of Lyme disease diagnoses in California T years after 2015. So we're not plugging anything in for T. T is our variable. We're just going to come up with an equation that can be used to calculate if you have the year. So for instance, if it was this year, which is 2024, we would say, well, that's 9 years later, and we would plug in a 9 for T to actually calculate. But we just want to write the equation right now. So we're going to say our initial amount is 250. Now our growth rate, because this is increasing, so it is a growth rate, is it's going up 40%. So remember, it's going to be 1 plus, and then 40% as a decimal is 0.4, where you move that decimal 2 places. So that's how you would write it like this. But we want to go ahead and simplify to get our growth rate as a single term. We don't want to have it as an expression there. So then I would rewrite that as 250 times 1.4 to the t. So that would be my equation. I'll highlight, color code here where I plugged everything. Oops. It's supposed to be highlight, not mark out. So there was my initial amount. There was my growth rate. And then I just simplified, and that was it. Now it says use the function to estimate the number of cases diagnosed in 2025. Well, that right there tells me since 2015 to 2025, that tells me it's been 10 years. So T is 10. So this is asking me to plug in a 10 for T and to calculate. So now you would just simply plug this into your calculator just like that, and it's going to pop the answer out for you. You do not have to do this by hand. So let's see. 250 times 1.4 to the power of 10. So that tells us, now we're talking about cases of Lyme disease. There's not going to be a fractional case. So we always are going to think about this scenario and if it makes sense to have a decimal or if you should be rounding up or rounding down. So this one is estimated number of cases. So we're going to round to the nearest whole number. So this 0.3, this would round down to 7,231. So I'm going to change my equal sign to an approximately sign. Remember when you have the wavy equal sign, that's approximately. And it was 7,231. And that was cases. In this next one, it says the value of a mechanic's car lift depreciates. Depreciate. That means it goes down in value. Appreciate goes up, depreciate goes down. So depreciates by 15% each year. A mechanic show purchased the new lift for 28. So that's the initial amount. So that's how much it originally cost. Write a function representing the depreciation of the shop's lift after T years. So to set this one up, we would say the initial amount is 2,800, and then it's going to be a minus because it is depreciating. It's going down. This is decay. So 1 minus, and then 15% as a decimal would be 0.15, and then our T years. So now I'm going to go ahead and simplify to get my decay factor. So 1 minus 0.15 is 0.85. And now I can tell my decay factors between 0 and 1, so I know that that's exponential decay. Now in B, it wants us to use that to determine how much the shop could expect to sell the lift for after 3 years. So that piece right there is telling us to plug in a 3 for T. So when I do that, I'm going to have my equation that we just came up with and plug in a 3 for T, and then the calculator is just going to pop that out for us. We don't have to do that by hand. So here that would come out to 0.85 to the third power. Now, this one is talking about money, so it makes sense to have a decimal to the hundredths place if we're talking about money. So this is 1719.55. $. So that would be the approximate value they can expect to sell the used lift after 3 years. Okay, so I'm going to stop this video here, and then I'll do a second video finishing the rest of the lesson. I'll go over the exit ticket and the next page of the notes. So y'all take a minute, try the exit ticket, and then you can go watch the second video.